Hello YouTube. Today we are going to talk about practical considerations about designing power transformers. For the purpose of this video we will restrict our discussion to less than 1 kVA transformers operating at 50 or 60 Hz and driven by a sine wave voltage source. To design such a transformer we need to know some basic data like the primary and secondary voltages, the operating frequency and the maximum apparent power the secondary will be able to supply. We need also less obvious data like the efficiency, which expresses the power transferred to the load in relation to the power drawn by the primary in terms of percentage, the peak magnetic field that is adequate for our application, and the current density that the wires can take. Apparent power means that we are considering not only the power that the load effectively consumes or dissipates, but also the power it may store. A pure reactive load such as a capacitor or an inductor will not ideally consume energy, but it will nevertheless draw a current in its process of exchange of stored energy. So when we are specifying the secondary power, we need to take this detail into consideration. The unit for apparent power is the volt-ampere or simply VA. This table gives an estimate for the efficiency as a function of the secondary power. These are not definite values, but starting points based on practice. As for the peak magnetic field, a good estimate is around 1 Tesla for regular non-grain-oriented laminated EI silicon steel if you want to keep core losses low. Some designs take advantage of higher core losses, especially those in which the transformer is going to work for brief periods at a time, like arc welder or microwave oven transformers, so they tolerate stronger magnetic fields. A starting point for current density is 3 amps per square millimeter for less than 500 VA and 2.5 for between 500 VA and 1 kVA transformers. The current density is a measure of how much amps you will let the wires carry for unit area. Lower current densities mean thicker wire which dissipates less power and keeps the transformer cooler at the expense of size and weight. That is why you must reduce the current density if your transformer is going to be encased somewhere with poor heat dissipation. Next thing to do is to calculate the number of turns for each winding and the dimensions of the core. From our previous video on power transformer modeling, we learned that the primary voltage can be written like this. Alternating voltages are normally rated by their RMS value, which is their peak value. That is, when the cosine of 2 pi ft is equal to 1 times the square root of 2 over 2. That way we can write the new relation in terms of RMS voltage. And considering that from now on all the voltages and currents will be treated by their RMS value, we can simply write it like this, without the RMS superscript. Considering that the frequency, the magnetic field and the area are the same, we can repeat this equation for the secondary, replacing the appropriate number of turns. And now I will gesture hypnotically and these equations will tell us the number of turns each winding will have. Note that although the turn ratio between the primary and secondary is determined by the relation between their voltages, the absolute number of turns for each winding is not arbitrary, since the other parameters in the denominator of each equation will impose their practical constraints. EI core laminations commonly have a fixed relation between their dimensions regardless of size. The most important dimension is the center leg width, A, from which you can easily calculate the other dimensions. This is because they are cut so as to avoid loss of material. You can obviously find DI laminations that do not conform to these proportions. Some of the most common widths for the center leg are the following. The other important dimension is the window area, which will accommodate the windings. In theory you could stack whatever number of laminations, but it is a good idea to start with a square cross-sectional area for the center leg because that is the geometry that allows maximum window area for a given overall size. So you pick one of the center leg widths and square it. That will be called the geometric area AG. One of the most common thicknesses for those laminations is 0.5 millimeters. They are covered on both sides with a 25 micrometer coat of insulating material so as to reduce eddy/focal currents. This will make 10% of the total thickness. You then multiply the area Ag by 0.9 in this case. That is called the magnetic area Am, and that is the area that we will effectively consider for our calculations. If you have seen our previous video on transformer modeling, you may be scratching your head because Am will not be equal to the internal area of the windings. Indeed. But the permeability of the ferromagnetic core is thousands of times greater than the permeability of the insulation, which means that the area the latter takes will not concentrate a great deal of magnetic field lines, so it can be neglected. Now that you have your initial guess for the magnetic area, you go back to the equations and get Np and Ns. We need to know if the core we have selected has a window area that can accommodate all the wire. The area taken up by the wire is the number of turns multiplied by the cross-sectional area of each wire. This must be less than 1/3 of the window area because you have to leave room for the airspace between each turn and the various insulating sheets between each winding layer. This relation is called fill factor. So the wire area should be equal or less than the window area times the fill factor. Young players should stick to 0.33, 1/3. Pros manage to squeeze it all in with a fill factor of 0.4. More than that, you need to be a ninja. If the wire area exceeds this calculation, you must choose a wider central leg and start all over again. If on the other hand the wire area is too small, this means that you chose too large a core. You just need to restart your calculations with smaller core and check again the wire area until you come close to the 1/3 fill factor. Let's then apply all of this to an example. In EEV blog number 279, How Not to Blow Up Your Oscilloscope, Dave talks about the use of an isolation transformer as a solution. We are going to try to design and build one. Before we proceed, however, it is important to note that this is not a step-by-step do-it-yourself video, just nerd entertainment. And to build a device like this you need to be a qualified professional or work under the supervision of one. Mains can kill, so you need to know what you are doing. Here is our basic data. Our secondary power will be 190.5 VA. Consulting our efficiency table, we can set efficiency to 90%. This will give us a primary power of 212 VA, which means we estimate the primary current to be 1.7 amps. Since we are under 500 VA, we will use a current density of 3 amps per square millimeter. So for the primary we would have to have a 0.56 square millimeter wire, and for the secondary we will need a 0.5 millimeter wire. Consulting a table of standard enameled wire gauge, there is a 0.52 square millimeter wire. This will be more than enough for the secondary. If we employ this same wire for the primary, the current density will be 3.3 amps per square millimeter, which is good enough. With practice you will know which initial EI core size to choose. A good rule of thumb is to extract the 4th root of the power rating. This will give you an initial guess for the center leg in centimeters. But it is only valid for laminations whose dimensions guard the relation we are discussing in this video. Our transformer is rated at 190.5 VA, which will give us 3.7 centimeters or 37 millimeters. The closest value from our table of available core sizes is 38 millimeters. With this we can calculate the number of turns for the primary and for the secondary. Notice that we cannot have a fraction of a turn. So the number of turns is rounded up or down to the nearest integer. Now we can calculate how much area the wire is going to take. The fill factor of 0.35 is not a comfortable figure. It turns out that we found a bobbin that has an internal area of 38 by 41 millimeters, which will allow us to stack a little more EI laminations, taking our magnetic area AM to 1,402 square millimeters. With this we can have just 340 turns. And now our fill factor will be 0.33. That's more like it. The wire we chose for both the primary and secondary has a diameter of 0.813 millimeters. But the bobbin has a span of 50 millimeters. This means that, considering the thickness of the wire insulation, kinks and bends, each turn will occupy an estimate 0.895 millimeters of that span. Each winding layer will then accommodate no more than 55 turns. We need to wind 340 turns. This means 6.2 layers. If we reduce from 340 to 330 turns to have exactly 6 layers, we will have an increase of 3% in our magnetic field, which will not, we hope, significantly increase our core losses. We can now calculate the primary and secondary wire resistance by assuming the medium length turn is 4A plus 2D, where A is the center leg width and D is the height of the lamination stack. This will be 234 millimeters times 330 turns. This will give us approximately 77 meters. A 0.52 square millimeter wire will feature a resistance per length of 0.0332 ohms per meter. Our windings will have a 2.6 ohm resistance or thereabouts. On the primary, this will represent a 4.42 voltage drop, and on the secondary additional 3.9 volts for a total of 8.32 volts at full load. This is approximately 6.6% of the nominal 127 volts, which is acceptable. We can directly sum the voltage drops because the turn ratio is 1:1. The general rule is that the voltage drop on the primary be divided by the turn ratio. Now for some applications, some more windings are added to the secondary to compensate for the voltage drop caused by the wire resistance at full load. In our case, doing so would make the secondary have an open circuit voltage that could exceed the main's nominal voltage. I decided to leave the secondary uncompensated, and if the voltage drop at full load occasionally becomes a problem, I can always use a variac to raise the voltage a little. Now that we have an estimate of the length of wire we need for the windings, we can calculate their weight and the silicon steel weight. A good estimate for the core loss type we chose is 2 watts per kilogram at 1 Tesla. But it is always a good practice to get this number from your manufacturer's datasheet. You must keep in mind that the core loss will always be there all the time, with or without a load. The wire loss, on the other hand, will be variable and will be maximum at full load. Now we can check if our calculations have led us to the efficiency we initially estimated. And bingo! With everything calculated, we can now go get the material we need to build our transformer. Thanks for watching. Have a good night and stay beautiful.